Everybody in the world has opened a can of soda at some stage and heard that fizzing sound as gas bubbles out. Gas dissolves in liquids, and this is critically important to the understanding of human and animal physiology, and it's also a major component of anesthesia practice. Fundamentals of Anesthesiology and Critical Care with me, your host, Pat Nelligan. This is a series on understanding gases and vapors, and we've moved on to the solubility of gases in liquids. This is part 1 on Henry's Law, and it will be relatively short. In the previous tutorial, we talked about the alveolar gas equation. In this tutorial, we're going to discuss gas solubility. I'm going to introduce you to this by discussing Henry's Law and the Ostwald solubility coefficient, and then we're going to move on to the solubility coefficients for oxygen, carbon dioxide, and nitrogen in extracellular fluid. You are very thirsty, so you buy yourself one of these. Inside the bottle is a semi-transparent liquid. It is still, there are no particles, there are no bubbles. You open the top and there is a fizzing sound, and then a bunch of bubbles rise to the surface. And bubbles appear throughout the decanted liquid. They fizz on your tongue. Now, everybody in the world knows that this fizz is carbon dioxide that is bubbling out of that liquid. You couldn't see it before. Where was it? And why did it bubble out now? The basis of this is a core topic in science known as Henry's Law, and anybody who works in any scientific field needs to understand this. And it's based on the concept that gas dissolves in liquid. Cold liquids hold more gas than warmer liquids. You know this if you've ever boiled water on a stove. You see bubbles of air leaving that water long before it reaches boiling point. The volume of gas dissolved is proportional to the partial pressure of the gas, the solubility, and the temperature. So whenever a gas coexists with a liquid, some of that gas dissolves in the liquid. That means that molecules of the gas disperse throughout the liquid. There are no bubbles of gas, and this is really important to understand. Oxygen and carbon dioxide, for example, exist as single molecules buried in liquids in the body. Gases can be forced into liquids under pressure. That's what happens when you use a soda stream or similar device. In this setting, carbon dioxide is forced into water, and then as soon as you've done that, a cap is immediately fitted and the gas is kept there under continued pressure. Gases diffuse from where they are in high pressure to where they are in low pressure. Hence, when you remove the cap, the gas rapidly leaves the liquid, forming bubbles. So gases diffuse out of solutions. If the partial pressure of the gas above the liquid is low, the gas will leave the liquid along the partial pressure gradient. If that pressure gradient is kept high, for example by applying a flow, then the gas clears quicker. The higher the flow, the quicker the gas clears. That's why you turn your flows up on the anesthetic machine to clear the volatile agent and/or nitrous oxide at the end of a case. The Ostwald solubility coefficient is a dimensionless measure that describes the solubility of a gas in a liquid. It is the ratio of the volume of gas at a specific temperature and pressure dissolved in a given volume of liquid when the liquid and gas phases are in equilibrium. So it's the volume of gas in a volume of liquid. For example, in water at 37 degrees Celsius at 1 atmosphere, and that's 760 millimeters of mercury or 101 kilopascals, the Ostwald solubility coefficient for oxygen is 0.31 mils per liter per millimeter of mercury and 0.226 mils per liter per kilopascal. If you multiply this by the atmospheric pressure, 760 or 101, depending on which you use millimeters of mercury or kilopascals, then you will find that there is, at this temperature, 24 mils of oxygen dissolved per litre of water. Going back to our litre of cola. 1 litre of soda, such as cola, contains 6.2 grams of carbon dioxide dissolved under pressure at room temperature, 20 degrees Celsius. How much carbon dioxide gas is dissolved? Let's work the problem. The molecular mass of carbon dioxide is 44 grams per mole. If you divide 6.2 by 44, then the result is 0.14 moles of carbon dioxide in that 6.2 grams that we have in the bottle. Now, 1 mole at standard temperature and pressure occupies 22.4 litres. That's known as the molar volume. If we multiply 0.14 times 22.4, then we will find that there are 3.15 litres of carbon dioxide in 1 litre of soda. Human plasma and extracellular fluid, they're similar but not identical, and indeed intracellular fluid, are not pure water. And these fluids have their own solubility coefficients for gases at 37 degrees Celsius. The solubility coefficient for oxygen in mils per litre per kilopascal is 0.23. I'll show you how this works out in the later tutorials. The solubility coefficient in mils per deciliter per millimeter of mercury is 0.003. Because kilopascals and millimeters of mercury are used throughout the world, sometimes interchangeably in different locations, in all of these tutorials I'm giving all of these numbers in both kilopascals and millimeters of mercury. You will note that nitrogen has a solubility coefficient of 0.012. That means that oxygen is 20 times as soluble as nitrogen. Conversely, the solubility coefficient for carbon dioxide is 5.18 or 0.068 mils per deciliter per millimeter of mercury. This means that carbon dioxide is 20 times more soluble than oxygen in body liquids. This is important. It's important in terms of basic physiology, but it's also very important in terms of how anesthetics work. The solubility of any gas or vapor has a huge impact on its onset of action and its offset of action. And how the body handles carbon dioxide and oxygen is a really good way of illustrating this. At this juncture, I need to make a key point that refers to all gases dissolved in liquid. The content of gas dissolved in a liquid is measured as a partial pressure in kilopascals or millimeters of mercury, not in millimoles per litre. Let's review this tutorial. In this tutorial, I introduced gas solubility and started with Henry's law. We moved on to the Ostwald solubility coefficient and then the solubility coefficients for oxygen, carbon dioxide, and nitrogen in extracellular fluid. In the next tutorial, we're going to talk about the solubility of carbon dioxide in the body. I'll see you then, and I guarantee you'll learn something.